Okay, thanks everyone for coming back. So we're about to start this next session. We're going to have the last talk of the second session. It's actually going to be, unfortunately, a pre-recorded talk, as Enrico couldn't be here because he was at the US Space Weather meeting. So it's pre-recorded, so hopefully we can get that teed up now. If there are any pressing questions, we can maybe try and take note of them, and then we can ask Enrico to comment on them afterwards, maybe. Clash of meetings, it's never good.
Hello, everybody. Thank you for the kind invitation to give this talk. Fortunately, I cannot be present in Sofia or online because I have a conflicting workshop this week. So I'm gonna present a work which has been published recently, last year in JGR, about using physics informed neural networks for data-driven discovery of the Fokker-Planck equation for the Hertz radiation belt electrons. And these are my co-authors, and this project has been supported by a NASA grant. So I'm just gonna sort of summarize radiation belt physics in a sense in one slide. Hopefully some of you are already familiar with some of this material. So the easiest way to understand electrons and ions trapped or quasi-trapped in the Earth's magnetosphere is to look at three adiabatic invariants. Each adiabatic invariant is associated with an orbit. So here on the right, you see the magnetic field line, and basically charged particles are trapped following three distinctive orbits. The first one is the gyro motion, which is just the gyration along magnetic field lines. And this is associated with the first adiabatic invariant, the magnetic moment. The second one is the bounce orbit, namely bouncing between one hemisphere and the other, where basically the bouncing point is called the mirror point. And this is associated with the second adiabatic invariant. And then finally, the particles go over an equatorial drift. The direction depends on the sign, so electrons drift one way and protons the other way, and this is associated with the third adiabatic invariant. So here on the left is a sort of a figure that shows the whole banana area, or the radiation belts, banana rings that are basically a sort of torus-shaped area surrounding Earth. Now, the focus of this talk is on what we call the radial diffusion equation, and I like to oftentimes to quote this quote from George Box that says all models are wrong, some are useful, because to me this equation, which is shown here, which is the radial diffusion equation, is really the prime example of a model which is wrong but useful. So there's a bit of nomenclature here. So F, which is our quantity of interest, is the phase space density in unit of flux over momentum. L, or L star, is the equatorial radial distance, and this is associated with the third adiabatic invariant in units of Earth's radii. T is time. VLL is the diffusion coefficient, and tau is an electron lifetime. So this equation comes as a reduced order model, if you wish, starting from a full 6D plus time Vlasov equation, and then going through what is called a quasi-linear assumption. And basically, this equation describes the evolution in adiabatic invariant space of the phase space density that diffuses through L. And so this assumes that the first two adiabatic invariants are fixed, are constant, but the third one is broken. And this is the simplest approximation, but very useful, because the third adiabatic invariant, which is the one associated with the drift, since the drift has the longest time scale, is the one that is easier to break. And this equation, in fact, has been the focus of intensive investigation in magnetospheric physics for more than 60 years, and this is just a few examples of landmark papers starting from the 60s that have studied this equation. The F over tau term there is a loss term that basically encodes all other non-diffusive losses, including the loss of when particle end up being in the loss cone and being lost due to impact with the atmosphere. And DLL, so in this approximation, basically DLL is radial diffusion, is the diffusion coefficient that basically encodes all of the physics of wave-particle interactions. So why is this model useful? For a number of reasons. So the first is the sort of following Occam's razor, and again, quoting this paper by George Box, since all models are wrong, the scientists cannot obtain a correct one by excessive elaboration. On the contrary, following William of Ockham, you should seek an economical description of natural phenomena. So in this sense, this is the simplest, possibly one of the simplest equations you can come up with. It's 1D in space plus time. So as I said, it's 1D plus time, so therefore it's computationally inexpensive, yet it's non-trivial. In fact, when you solve this, a very rich family of solutions can be recovered as long as tau, the electron lifetime here, is general enough. And finally, it's physics-based. It's not just an empirical relationship, but as I said, it can be derived from first principle from the Blasov equation. And indeed, it contains most of the physics responsible for the particle dynamics. And in fact, it has been proved successful in many cases. It's been the focus on investigation, as I said, for more than for several decades. Now, why is wrong on the other hand? And here, wrong has to be understood sort of from the physicist sense. It's wrong because it's an approximation, and so radial diffusion is derived within the kinetic quasi-linear theory. There are a number of assumptions. I'm not going to go through any of these. And in fact, there has been a number of papers focusing on non-resonant heating, while the quasi-linear theory only captures resonant wave-particle interaction in the diffusion coefficient. And even when all these assumptions actually hold and quasi-linear theory works fine, there are multiple sources of uncertainties in estimating the radial diffusion coefficients. For instance, you have to assume there's a given value of the background magnetic field model. Typically, bounce and drift averages are applied, so there's no MLT dependence, and so on. And for this reason, in fact, if you look at the literature, there has been a multitude of parameterizations. Possibly the most popular went back to 2000, the Broughton and Albert parameterization, but more recently, some other papers have suggested different parameterizations. And so a good reference I'd like to cite is this paper by Bentley et al. That it's about capturing uncertainty in magnetospheric UFL wave models. Now, the focus of this work is to solve an inverse problem, and this is the inverse problem statement. So, starting again from this fundamental equation, which is in a sense is a simple diffusion equation, we have two free parameters, DLL and tau. So one might ask, what is the optimal choice of parameters, DLL and tau, that makes the result of the diffusion equation most consistent with data? It's an inverse problem because we know the result. We can sort of measure or estimate F from data, like from Van Allen probes data, and we want to infer the inputs or the parameters, DLL and tau, which usually it's a much harder problem than the forward model, because one of the simple reasons why this is hard, where there's no closed solution, and oftentimes there's no unique solution. In fact, the problem is ill-posed. Now, the standard way of solving an inverse problem in geophysics is by following a Bayesian parameter estimation approach. And the reason being the following: because the underlying model is wrong, there is not a unique solution, as I just said, so it makes sense to look for a distribution of parameters. So this is a classical topic in geoscience. Maybe it's not yet a mainstream approach in space physics. I haven't seen many papers applying Bayesian parameter estimation. This is an example, this paper that a postdoc working with me a few years back published when we actually applied this approach with Monte Carlo, Markov chain Monte Carlo on exactly this problem. A downside of that approach is that it's difficult to apply in higher dimension, but in this case it was 1D, so it worked well. You still have somehow, however, to rely on a parameterization of the diffusion coefficient and the electron lifetime, where in this case, again, with the Bayesian approach, each coefficient is a random variable. And we follow the following parameterization. So for DLL, this is exactly the same parameterization used in the Brautigam and Albert paper, except that we allow for these parameters alpha, beta, and B to be random variables. And then tau is parameterized as a polynomial with two different parameterizations for L, smaller or larger than LPP, the plasma pose location. Once you run the Markov chain Monte Carlo procedure, this yields the optimal distribution, what is called the posterior distribution of the coefficients. And those are an example of the distribution for 6 of these free parameters. And therefore, from those distributions, then you can run ensemble and do uncertainty quantification and so on. Now, the focus of this talk, however, is using a different approach that came up recently in basically 2019. This paper was published about physics-informed neural networks, and already this might be kind of outdated by now. This got a very large number of citations in only a few years, and this indicates how important this method is. So I'm gonna summarize physics-informed neural networks, or PIN, in just one slide. And the idea, it's actually very simple, and it's the following. So this is a neural network. As all neural network, one of the important components is to define a cost function. And typically the cost function, when you use a neural network with some sort of data or ground truth, you try to optimize a norm or an error between f, which here would be the output of your neural network, and f observation. So you try to minimize the distance between the neural network output and observation in maybe a L2 norm or a mean square error or something like that. The important idea here is that so we still have this second term in the cost function, but we also include a partial differential equation that we want to solve in the cost function. And this is the square bracket here. Basically, we have a number of points or collocation points where we use for training the network. And on top of trying to minimize the error with respect to the observation, we want the solution f to be a solution of a given partial differential equation. Now, the way to do this, the trick under the hood, is called autodiff, or automatic differentiation. And it boils down to the fact that all derivatives here, like df dt and d over dl, are computed exactly using the chain rules, which is exactly the same way a neural network backpropagates its error. Except that here, instead of taking derivatives with respect to the weights and biases of the network, you take derivatives with respect to the inputs. And you can think that this can be done because typically the output of a neural network is analytical and differentiable function, even though the network may be complex and deep, but it's just a superposition of elementary functions, so you can always differentiate those. So PINs is both a gridless method to solve a PDE on a set of points, so you can use this in a forward way to solve a given PDE, or, and this is the way we're going to use here, it's a way of estimating the coefficients of a PDE, so a way to solve an inverse problem. And how does that work? How does PIN work for parameter estimation? So this is a sort of a very general framework. Assume you have a PDE of this form, df over dt plus h, which is a nonlinear operator that is applied on f, and dc, where d and c are free parameters. So of course x and t are space and time. The way this works is the following. We can define 3 independent networks. Each of the network takes as inputs a location in your domain in space and time. So basically one value for x, if this is just a 1D example, and one value for t. And each of these network outputs respectively f, d, and c. And as these three numbers are sort of lumped together in the loss function, it once again is a sum of two terms. One is the standard mean square error with respect to observation, and the other is the residual of the PD that we want to solve. And by means of training these, and when this kind of back propagates, you end up training these three different networks at once, when you basically the output of which is the optimal value of F, optimal value of D, and optimal value of C. And this way, you have solved your inverse problem. Now, there's a big caveat here, which is the following. The standard equation for radial diffusion I was talking about is this one on the top. So now this framework allows you to have a very, very general form of DLL and tau. In fact, they can be simply any function of space and time. However, by doing that, this equation becomes too ill-posed to even make sense for an inverse problem. And you can realize that just by thinking that you can plug in, for instance, in DLL, you can plug in any function of space and time. Now you have F from your observation, so you can solve for the left-hand side and for the first term on the right-hand side, and you can invert these sort of automatically by, so you can get tau. So in other words, there are infinite combinations of DLL and tau that can give you the same result. So it's just too much ill-posed to make sense. So what we've done instead is to sort of take a step back before getting into the diffusion equation. You can use a more general form of a Fokker-Planck equation, which, by the way, can also be derived pretty much the same way from Blasov. And therefore, so what we've done here is to have a different equation, a more general equation, where the diffusion term is exactly the same, but we have replaced this F over tau term, which again causes too much generality and too much imposedness, into an advection term. So instead of tau, we have a drift coefficient C, and we have an advection term here. Now, of course, every time you propose a new method, it's a good idea to compare against some baseline models. In this case, we have used these three models. Again, the first one has been published in 2000, Brattingham and Albert, and the other two are more recent, MOSAIICS et al., JGR, and Ali et al., also JGR. And those are the parameterization they use for DLL. And you can notice that although they are very different forms, each one of those three parameterizes DLL as a function of L and Kp being the geometric index. And for tau, we have used this other very simple parameterization, which divides tau in two regions, L smaller or larger than the plasma pose location. And this has been used a lot in the literature, I guess, starting from Spritz et al. In 2005. The plasma pose location here is estimating using this approximation, which is an empirical approximation by Carpenter and Anderson. And then maybe a technical detail is that when we solve this in a forward way, the forward model, we used a second order modified Crank-Nicholson finite difference scheme. The details can be found in this paper. And the reason being that once you have a varying coefficient DLL, it's a good idea to have an unconditionally stable model. All right, we also, aside from the baselines, we also need some definition of errors of some metrics we're going to use. And we have these three definition of errors, which have actually been taken or inspired by a paper by Steve Morley. The percentage symmetric accuracy, this is a metric for accuracy, where pk is the kth percentile. F and f hat are the ground truth values taken by observation, and the corresponding values produced by a model. This on the right, it's a different metric to measure bias, again as a percentage. And then the one on the bottom is the relative error of the log of phase space density. So this is just the relative error f with respect to f hat. Again, f hat is the ground truth, but in log space, reason being that f actually ranges several orders of magnitude. And now, in principle, you can calculate this point by point in your domain, but we want to have an error which is just a function of L. So we actually integrate out the time domain, just taking the median value. All right, this is the data we've used for this study. It's Van Allen probes data. It's about 4 years of data for a given value of mu and k for first and second adiabatic invariants. There are about 500,000 data points. And more or less arbitrarily, we have divided this data set into training and validation the first 3 years, and test is the last 4th year. And what is shown here as a scatter plot, as a heat map, is the log of the PSD, which would be f in our equation. Okay, there's always, when you train a neural network, and PIN is no difference, there's always some degree of stochasticity, which has to do mostly with the way you initialize your network. So what we've done here is to train 20 different pins and to choose the best 5 solution, where we have used epsilon, the relative error, as our metric to define the best solutions. And those are on the top row, the diffusion coefficient, and on the bottom row, the drift coefficient for each one of these 5 best realizations. And you can see that, the general global scale features are very similar. The fine scale details might actually differ quite a lot. Now, when we use those, well, first of all, we have these 5 realization, but at the end of the day, we just want to have a single solution to feed into our forward model. So the simplest approach you could think of is just to take the average of those, and that's what we did. And this figure here on the right shows the average of the best 5 diffusion coefficient and drift coefficient, and this is what we're going to use as the solution of the inverse problem. And one important characteristic of using pins, again, compare, for instance, with the Bayesian approximation, is that now we have a value, an optimal value for DLL and C as a function of time and space all over our training data set. Now, when we use this in a forward model, maybe not surprisingly, this gives us very good results. So the black line are each one of these best 5 realization. The red line is the ensemble mean, where here on the vertical is L, and epsilon is the error, so the error as a function of L. While the other 3 lines are those 3 baseline, and you can see that they're all much worse than the solution computed with those pin-derived coefficients. Again, this is not surprising, because this is exactly what the pin does, is to find the coefficients that actually minimize some sort of error. So this is the result of the training set. On the other hand, once we have this specification of the coefficients everywhere in space and time, this is really all we need to do some sort of data mining and to also understand the physics. So in other words, all the information about the physics of interest is somehow embedded in these 2 coefficients. Now, as long as we believe that the equation we start with is representative of the physics. And that's exactly what we've done. And of course, more details are in the paper. We run, first of all, a statistical analysis of the coefficients. So for instance, we look at how DLL, or again, working log space, the log of DLL changes as a function of L. And so the median value is this orange line here. The gray area covers the 25th to 75th percentile. And just to compare, the purple line here is, well, actually the yellow line to start with is DLL proportional to L to the power of 10, which is exactly what the Broughton-Albert approximation uses. And here's just to show that maybe this simple parameterization is good for small values of L, but then maybe L to the 20 is probably better for larger values of L. What is shown here is a different way of visualizing this information. It's a rank distribution of the diffusion coefficient, again in log space. So the idea here is to, for any given value of L, so it's sort of condition on a value of L, you can rank, so where it's yellow, red, or black, this is rank equal number 1, meaning that the most of the time, most of the realization end up being in that bin. Of course, L or log of DLL is binned in different values. So this kind of shows different possible realizations of DLL or different trajectories in this space. Similarly, for C, so okay, maybe one comment I can make on DLL is that we can see that there are at least 2 or 3 different regimes that this curve follows. It's similar for C. There's a larger error here at the larger boundary condition. Something I didn't mention is that as a boundary condition, we use L between 2 and 5.5. And again, there are, to the very least, 2 different regimes here with sort of a knee around 3 or 3.5. And this is very clear on the right plot. There are very different realizations of the drift coefficient C. Okay, something else we can do once we have this information is to run what in machine learning is called a feature selection. So we use a very simple model, a generalized linear model, and we use backward elimination method, which means that you have this number of features which are here on this plot, and then you can eliminate one at a time to sort of have a ranking of importance, feature importance. And so these plots are to be read from left to right. This will be what is the R squared, the coefficient of determination for a model that only uses, for instance, L. Here is the first feature. And you can see that already for DLL, you already get almost 95% only using L. Then what happens when you add the second feature, which in this case for DLL is L times an average over L of the PSD, and so on, and you can rank different features. The important point here is the KP, which, as I mentioned earlier, is one of the important parameterization parameters for all these baseline models. Well, for C is not even in the first 10, I believe, and for DLL is number 6. So what we try to achieve here is to come up with a parameterization that actually does not use KP. So the next question is, can we forecast unseen data using this technique? So now we have, once we have done a feature selection on this parameter, what we can do is to train yet another machine learning model. In our case, we've used an ensemble of decision trees with gradient boosting to actually predict the coefficients DLL and C. And we ended up using only these 1, 2, 3, 4, well, 5 inputs, because boundary conditions are 2 different values. And we didn't use KP, as I said. This is different from all other parameterization. The reason being because if you want to use KP to forecast unseen data, you need to be able to forecast KP first. So it sort of only shifts the problem into a good prediction of KP. Now, sort of a technical detail here, one of the parameters is the log value of PSD, which is F, which is the unknown. So using this as an input makes the problem nonlinear, because now the diffusion and drift coefficients are function of the solution, and therefore to solve this numerically as a forward model, you need something as a predictor-corrector method or any other nonlinear method. This is a summary of the parameter estimation pipeline. So we start with an assumption that the physics obeys a Fokker-Planck equation of this form. It's a drift diffusion equation. We use spin to estimate the optimal coefficients in a given on a given training set. We run a feature selection, so to understand how can we parameterize or model these coefficients D and C. And then we train a different machine learning model that predicts DLL and C at any given time in the future. And then you can, once you have this estimate of DLL and C, you can plug those in back into your equation and you can solve this forward in time. This is the result on the test set. As I said earlier, it was not surprising that it worked well on the training set, but now this is really the main result. That when we plot this on the test set, which is the unseen data, none of this data has been used in any of the previous process or learning. Now again, this is the epsilon, this relative error as a function of L. You can see the pin is the black line, and once again, it's better or comparable to the baseline. And this is how epsilon looks like if you do a 2D heat map on the test set in time and space. So this on the left is the result of this work, and the other three are the baseline. Those are two vertical cut for different values of L equal 5 and 4. And once again, here the blue line is the data, the Allen probes data, and the purple is the result from the pin parameterization, which is better than the baselines. Okay, now the sort of step further we are interested in is what I call the sort of, in a sense, the final frontier is to do interpretable AI. So in the pipeline that I just described, there's still sort of a black box component, which is we needed to train a machine learning model, which again was opaque, black box, in order to estimate the future values of the DLL and C. What we tried next is to say, okay, why instead of that we just approximate DLL and C with the simplest approximation you can think of, and knowing that from feature importance that L, which is the spatial coordinate, is the single most important parameter, we thought, okay, why don't we just do a cubic interpolation in log space? And this is the result of the cubic interpolation. And if we look at this cubic interpolation in space, this is the black line here for C on the right and DLL on the left. And you can see that, in fact, captures pretty well at least the median value of these two coefficients. So now, using this parameterization, this is interesting because now we can plug those parameterization in the initial equation, and the equation becomes parameters free. It is only function of the boundary conditions, basically, and it's a 1D in space plus time ODE. And those are the results now using these other two metrics, the symmetric percentage accuracy and the bias. And the black line is the pin. Now the accuracy you can define with some given error bars. While the bias, you can't really apply error bars here. But in either cases, you can see that the black dots and associated error bars are again comparable or smaller than the other two baselines. In this case, we didn't even use the Ali et al. Because it was just out of scale, the errors. Once again, this is just using the simplest parameterization that we have learned using this pipeline of pin and inverse problem and so on. Another thing you can look at, and I'm about to conclude here, is the diffusion versus drift. So trying to understand a bit more of the physics that is going on. We have these two terms in our equation. One is the diffusion operator, and the other is the drift term. And we can compute the ratio of the two, which we call R. And we plot here in log scale as a function of L. So anytime this is close to 0, it means that there's an equal sort of balance between the diffusion drift terms. So they are of the same order of magnitudes. And then you can see that when you go to larger and larger values of L, so the more outer radiation belt, this gets smaller, meaning that the process becomes more and more diffusive, and the drift becomes less important. And finally, something that I think it's very interesting that one can do with this approach is automatic event identification. So once you have trained your pin, you can actually, in your training set, in your domain, you can, as I mentioned, the cost function is defined as the sum of the two terms. You can just look at the term that defines the error or the residual of the equation, and you can see how large this residual is anywhere in space and time. And what is shown here is, okay, there's a bit of normalization and saturation of colors just to make it more clear. But basically, all these red dashed lines here denotes time in the training interval when the residual of the PDE was in the 99th percentile of its distribution. So this is another way of saying, these are times when the PDE is not very well solved. So the neural network couldn't find a solution that both agrees with the data and the PDE. In other words, this is a time when a simple drift diffusion equation does not work. And this opens a lot of avenues for physics discovery, because this tells you, look, there's something else going on, for instance, nonlinear mechanism of non-resonant interactions and so on. And what we've done, so this plot on the left was sort of computed automatically just looking at this 99th percentile, and we end up with about a dozen time periods. And then we look at those time periods and we try to see if those were studied in the literature. And in fact, most of them, but not all, have a number of associated papers that actually studied those, either had to do with CME or with dropout events or sudden particle enhancement. So this is an indication that in fact the simple quasi-linear drift diffusion approximation was not valid during those times. What I'd like to propose here to the community is there are a few intervals for which I couldn't find any paper, so maybe there's something more to learn and study from random props data doing this automatic event identification. Okay, I think I'm about to finish. So just some conclusions. I believe that physics-informed neural network is really a game changer in applied math. It's possibly the best way we can use it in space physics is to solve inverse problems, the way I just showed. So in this, I just presented a use case for a derivation of diffusion and drift coefficients for radial transport. You can do a number of things with PIN. Some of them I didn't even mention, but you can assess when quasi-linear assumptions are not valid. You can identify automatically interesting events. In principle, you can even redefine or reparameterize an electron lifetime. You can improve the accuracy in nowcasting and forecasting without having to use future KP values. And then eventually you can reparameterize the diffusion and drift coefficients with some simple interpretable relationship. Okay, this is an old slide, so the preprint. Actually, this has now been published. This is the URL on JGR. This on the bottom is my email. Again, I apologize for not being able to answer questions live, but please feel free to reach out. I'm always happy to talk about this work or in general any machine learning approaches to space weather. And with this, thank you very much for your time.